Welcome ENET 130, Semiconductors at Bellingham Technical College. We are in Chapter 7 of James Fiore's Semiconductor Devices and are going to launch into small signal amplification with bipolar junction transistor amplifiers. In Chapter 6, we defined some characteristics of general amplifiers, and now we're going to apply these specifically to ones that we can design and analyze with everything we've learned about bipolar junction transistors and their surrounding circuits. So we've already defined BJT amplifiers in their DC mode. We've looked at biasing, what's necessary in the way of resistors and DC voltage supplies applied to the base, emitter, or collector to ensure that when we put a signal in at the base, it will open our base emitter junction, overcome whatever our forward bias voltage, probably 0.7, without losing part of the signal. We've defined the DC load line in terms of our voltage current capabilities, collector current and voltage across the collector emitter junction, and we've defined our Q point of the transistor operation, our actual voltage drop over the collector emitter, and our collector current DC, all of this DC for where our circuit is operating. So now that all of this was basically to set us up to allow us to insert a sinusoidal or other time varying signal, a periodic signal, into the base and then get another signal out somewhere else. And in one variation we're going to put a signal in at a different lead of our BJT and collect our signal elsewhere, but generally speaking we'll be putting signals in at the base. So with that said, we are going to have to superimpose an AC version of our same circuit model that we've been using so far in order to deal with our AC signal that we're amplifying. So for the first time we are actually going to use our amplifier circuits to amplify. So to do that we need a new circuit model. If you remember, we use the Ebers-Moll DC model of our bipolar junction transistor, a DC voltage source in series with a diode, basically representing the collector emitter gain in terms of the current source, and then the diode representing the base emitter junction. We're going to create a similar model to represent the way that our bipolar junction transistor responds to AC signals. Then we're going to superimpose that on the DC and actually use that model to go through some simple Kirchhoff's voltage law loops and define our gains and our input and output impedance for different common configurations. Okay, so let's dive into our AC version of our bipolar junction transistor model and look at how we're going to use it for signal amplification. Start by looking back at the base emitter junction. Now with DC we modeled this as just a diode. There was a fixed voltage drop in the direction of conventional current, but with AC we've got current kind of flowing in both directions. As our signal comes in, sometimes it's forward, sometimes it's reverse. And because of that, that same base emitter junction doesn't feel like a diode. It doesn't act like a voltage source. It actually acts like a little tiny resistor. And to get the value of that resistance, we have to go way back to our diode equation. So this is our diode equation telling us what the voltage drop over our diode is versus the input voltage, and in this case, because that voltage drop is over our base emitter junction and the current flowing across that junction is actually our collector current, we're going to represent it as the base emitter voltage drop versus the collector current in terms of what we're going to use in our amplifier. But this equation should look real similar, and it's what we used to model our current voltage behavior of diodes. So it's back to our exponential relationship. And in this case, the way we're going to use this equation is we're going to define a slope somewhere at a given operating point, because the slope really, if we want to apply Ohm's law, the slope of this curve at any point is in fact the resistance of that junction, because remember, if we multiply resistance times current, we get voltage. We can define the rise over run slope here as what's effectively the inverse of the voltage. And so we can define the resistance of that junction to our AC signal that's coming in at the base or coming in at the emitter. So we're going to model, instead of a diode, our base emitter junction is going to be the inverse of the slope of the current versus voltage characteristic of our base emitter junction, which is a diode. So we're going to go back to our old diode equation, define the slope, and then our first task when we define our AC model is to figure out our collector current, because the slope changes depending on where we are. And that will be one big component of the way we model our BJT from the viewpoint of our AC signal. So I'm not going to step through this proof too much, because you've seen this equation and you can go through this. But key points to remember: this is the diode equation. It also represents collector current versus base emitter voltage drop, because the base emitter junction is a diode. The slope varies depending on what the collector current is flowing through the transistor. And the resistance to that current flow is the inverse of the slope. And for those of you who have taken some calculus, you know that the slope is the first derivative of a function. And so you can actually take the first derivative of this equation with respect to the base emitter voltage, and you end up getting this expression, which actually includes the original expression if you're familiar with derivatives of the exponent function. But you don't have to be to use this, because for our algebra students studying ENET here, we can end up with this relationship. So after doing some math to define the slope, we find that at room temperature, we can define that resistance of the base emitter junction as being 1 over 38.6 volts times whatever the collector current is. If you're interested in how we got this equation, you can step through the math, but you don't have to step through the math. You can just use this equation. And this is valid at room temperature. If you want to operate your BJT at a higher temperature, you're going to need to go back and plug in a temperature in the original diode equation. We will be operating at room temperature in this course, so you can just use this equation. So we have a little r to indicate that there's a resistance to an AC signal. So this says the resistance of the base emitter junction to an AC signal going between the base and the emitter is equal to 1 over 38.6 volts times the collector current. So that's basically 1 over effectively a conductance. So we will use this equation every time we create an AC model. Okay, so let's compare our BJT DC model and our AC model. So we're used to this model for our bipolar junction transistors. So we have our collector, and then we have a DC voltage source, which has a defined ratio. We have, current source, an I with an arrow. It's a current source. And so it's giving us a current that's equal to the transistor beta times whatever our DC current is into our base. So BJTs are current gain devices. And then of course we have our diode representing the base emitter junction forward voltage drop. So here's our AC model, the same thing. So this time we have an AC current source. Now it's got the same ratio, but this time the currents are defined in terms of our AC signal that we're putting in. So the current amplitude of whatever signal we're putting in at the base times the transistor beta, and so beta is the same. So beta on the AC model and beta on the DC model are the same, is going to be the value of this AC current source that we're representing here between the collector and the base. Important things to remember about current sources. They have almost infinite impedance. So if we're ever looking at defining input or output impedance, and we're looking at a signal possibly traveling through the current source, we can assume they're an open from that standpoint. So that's an important characteristic we'll use. And then here's our inverse slope of the current voltage curve from our diode equation that we just defined on the previous page. So it's taking the place of this diode. So basically it's a pretty simple model. A current source in series with what is going to end up as a fairly small resistor, and then a signal will generally come in on the base or the emitter, and we're just going to insert this into the rest of our external circuit model and make some adjustments for the way our AC signal will see the rest of the circuit. And we will do that in just a minute. So before we dive into that, let's just name the three different amplifier configurations that we're going to look at. These are the three classical small signal bipolar junction transistor amplifiers. We will actually derive the voltage gain and in some cases input-output impedance for all of them, and go through a couple of examples with real numbers. But these are the general characteristics. They all have the word common in them. And in this case, common means whatever terminal of the BJT is not being used for signal in or output. So it does not always mean it's going to be grounded, so electrically common per se, but it doesn't have a signal coming in or going out. So first one is common emitter. So we're going to apply input to the base, and we're going to get an output at the collector. So the emitter is the one that's left, so it's common emitter. It will give you both current and voltage gain, and most importantly, it gives an inverted output. So that's kind of what's unique about it versus the other two. So our output signal is going to be 180 degrees out of phase with our input. So mirror image. There's the common collector, otherwise known as the voltage follower. Again, we apply an input at the base, but this time we're going to take our output at the emitter. It's known as the voltage follower because it has a current gain much more than 1, but a voltage gain of 1. So it gives you the same voltage output. So the gain in this case is realized in the form of current. We'll have a power increase, but with voltage staying the same, we're going to boost the current. So we can get a much higher current, but we retain the same voltage. And we get a non-inverted input. So the output is in phase with the input, 0-degree phase angle between the two. And last but not least is common base. So here we apply the input signal at the emitter, and we get the output at the collector. So the base is odd man out, so it's common base. This time it's kind of the inverse of the common collector. We have a current gain of approximately 1, but our effective power gain is all realized in voltage. So we get a very high voltage gain. So of the three, common base gives you kind of unity gain in current, but a real high gain in voltage. Also non-inverted output. Common collector gives you unity gain in voltage, high current gain, non-inverted output. And common emitter gives you some moderate current and voltage gain, but an inverted output. And the consequences of these configurations on gain and inversion fall right out of what we're going to look at with our Kirchhoff's voltage law loops as we go around the circuits. So these characteristics literally fall out of the math of just applying our good old Ohm's law around our circuit loops. We can use any DC biasing arrangement with any of the signal configurations. So we can apply our supply voltages at emitter, base, and collector and resistor arrangements in any particular configuration to make sure whatever signal we put in at whatever lead opens our base emitter junction and doesn't get attenuated. So we don't have to use a voltage divider or a two-source supply or anything in particular with one of these. We can use with any. Okay. The common designations with configuration don't really apply to our DC biasing. They apply to our AC signal only. Okay. So we're going to focus on common emitter. It's a good test case to use to understand things. And so we're going to define how we set up our DC versus our AC models and walk through the math of deriving and then utilizing our gain equations in the context of this, and then we'll apply that same logic to our other two modes. So we're going to start with a common emitter. We're going to have a two supply bias, and it's a little bit easier to understand than the voltage divider. And we're going to have an AC signal input, and we're going to take our output over a load resistor. So we're going to have some loading effects. We explored that in our general amplifier theory. And we're going to separate AC from DC with coupling capacitors. So we talked about attenuating our gain in DC with amplifier concepts. As the frequency went down, we dropped our gain. And that's because of these coupling capacitors. But they're essential because we don't want our AC and DC signals to necessarily get mixed up. So our coupling capacitors keep those straight. We'll see how they work. We're gonna divide the effect of the emitter resistor into portions that both the DC and AC signal pass through versus, and that's the swamping resistor, versus the portion that is only used for biasing. So we'll end up breaking up our emitter resistor into two series resistors, and then the rest of it is pretty much the same. So that said, here is a schematic. We'll zoom out a bit because it's such a big schematic. This is the whole amplifier with both AC and DC components. So this is a schematic that would basically give values for supply voltages and resistors and coupling capacitors. So if we start up on the collector end, we start at ground, and then we are going to raise our DC voltage with our VCC, our DC biasing supply at the collector. So current would flow through that from that source, DC current, through our collector resistor, and then enter the bipolar junction transistor at the collector. We have our load resistor out here, and it's separated with a coupling capacitor because we don't want our DC to flow from this bias supply out over our load. We only want signal over our load. So we've got a coupling capacitor that basically says, nope, only AC can come out to the load. So, because remember, DC will see a capacitor like an open. Going through our transistor, designations as normal. So we're going to have two series resistors, one what we call a swamping resistor. Then we're going to have a coupling capacitor to ground. So if we happen to have an AC signal, it would pass over this resistor and then go straight to ground. Our biasing, though, is going to travel through another resistor, and then they're going to step it up to get back to ground. So we've got a couple of biasing supplies, a VCC and a VEE. But this R big E only is involved in our DC. And I'll give a word here about capital letters versus small letters. In general, and this is referring back to the very beginning of the class where we had some notation, this is where we're going to use it. Lowercase letters generally refer to AC. So little r's are resistors that are acting only on the AC signal. A big R means it's acting on the DC. Obviously, if both types of signals are flowing through, it can act on either one. But that's to distinguish components that are truly specific to just one. So for instance, our V in, that's a little v because it's only an AC signal. And then our base resistor and coupling capacitor over here. So our signal comes in and it passes straight through that coupling capacitor because it's an AC signal. It's got some high frequency, so yeah, there are very little capacitive reactance. But a DC signal would not flow back through into our input supply, whatever it is. Okay, so this is what we'd see on a circuit schematic, or we'd open up a device and we'd see these physical components laid out in some arrangement. So our first step to getting our AC only model is to go through a few kind of checklist steps. So first thing we're going to do is we're going to short all the capacitors. because AC signals, don't see really any impedance from the capacitors. The capacitor values are chosen such that they pretty much are going to act as shorts for whatever frequency of signal we're using. Next, we're going to replace all the DC sources with shorts to ground. Because of a battery or a DC power supply, it doesn't provide any impediment to an AC signal. The water's only flowing uphill in one direction from the standpoint of DC. They act like a short. So all of these voltage supplies will just go away with a dead short to ground. We're going to use our AC current source plus our little RE to represent the resistance of the base emitter junction, to represent our BJT. So we'll use our AC model of the BJT. And we're going to take a look at how our AC current would flow to ground at the collector and the emitter. So number 4 here, our big R sub E is going to go away in the case of this particular circuit, because an AC signal is going to flow right to ground through this coupling capacitor. So this whole part of the circuit goes away. And because from the standpoint of the load, looking at the way current would flow, from the standpoint of AC, really this collector resistor and the load resistor are truly in parallel. So if we're looking at gain, we're actually going to put the load resistor and the collector resistor in parallel when we define voltage drop from the purposes of gain calculations. Because they truly are from the standpoint of AC, not from DC, but from the standpoint of an AC model, these two are in parallel. When we look from the standpoint of output impedance, we're actually starting on the other side of the coupling capacitor, so RC and RL are not in parallel, but from the standpoint of gain they are. So that's kind of our last step to creating our AC model. So this whole schematic from the standpoint of our AC signal becomes this. Much simpler. So I'll draw a few circles here. So here's where our BJT is. Basically this, everything in the red is our transistor. So here's our collector input, here's our AC current source, here's our base, and here's our little resistor, little RE, representing the resistance of our base emitter junction to an AC current. Here's little RE, which is representing this resistor up here, because it's the only one the current is going to, the AC current is going to flow through. Little RC, which in this case is the same as the R sub C and R sub L in parallel. And the base is pretty much the same. All capacitors have been shorted, and so AC can flow. So very simple model. So now it's not too hard to walk our way through this model and apply, our basic Kirchhoff's voltage law and Ohm's law to calculate currents and voltages at different points. And so we're going to use that to calculate gain of our AC signal. You might ask, well, why did I need to learn all that stuff about DC if I'm just going to use this nice simple AC model? Well, the DC model comes in handy in for one thing. Remember, we need to know what the DC collector current is to calculate our R little e. Because as it turns out, our entire AC model and our entire DC model overlap at one critical point, and that's the Q point. So we'll define an AC load line later on in the Class A amplifier section of the course, which is the very last section actually, and show that we can use this kind of model just the way we used our DC model and calculate a maximum magnitude of collector current and collector emitter voltage drop for the AC model only. It has a different slope, but it shares a common point with the DC load line at the Q point. So we know that our DC collector current and our AC collector current are common at that point. So if we calculate our ICQ, our actual DC collector current that's flowing at the operating point, then we know the current that we're going to use to calculate our R little e. And so basically we need our entire DC model does nothing but give us our R little e. But it's very critical because R little e is pretty much a big key term in defining gain. So it's definitely worth doing. Okay, speaking of gain, let's go ahead and define the gain of the common emitter configuration that we have here. So to do that, let's refresh ourselves. What is gain? Well, we're going to look at voltage gain. So it's V out over V in. Which in this case, let's see, what was V in? Well, here's our input voltage, and it is a common potential with the base. So the voltage versus ground of the base is V in. Well, that's handy. And we can also notice that we're going to take our signal out at the collector. That's definition of common collector. So the voltage at the collector versus ground is our voltage out. So V out over V in is the same as the AC voltage at the collector divided by the AC voltage at the base. Okay, so let's go ahead and use Ohm's law to calculate what that is in terms of collector emitter currents and resistors in our AC model. Very similar to what we did with biasing in DC. So let's start by defining our V sub C in terms of collector current and our little rc. So if we start at ground, here's our collector, and the current flowing through this path is the collector current. So V sub C is equal to collector current times the collector resistor. We can do the same thing down here. We can start at ground and we can define the voltage at the emitter. So that's simply going to be, we need the voltage of the base. We got to go up another resistor. It's V sub B, not V sub E. So we got to flow that current over another resistor. So V sub B, voltage of the base, which is V in, is going to be the emitter current dropped over these two resistors. So we start at 0 volts and we have 2 voltage drops to get to B. So it's emitter current times our R little e that is part of our transistor model, plus the emitter resistor that our AC current actually flows through. Okay? Well, an AC model works the same way as a DC model in a transistor, in a BJT. So base current is still very small, so our emitter and collector currents are pretty much the same. So we can substitute I sub E equals I sub C, and that lets us cancel these two currents, and we're left with a voltage gain being equal to negative R sub C over R little e plus R big E. Now, where'd this negative come from? Well, because the current's flowing this way. So if we start at 0 volts at ground, we actually drop voltage due to the direction of conventional current flow through our R sub C resistor. So V sub C is less than ground, whereas the base voltage, we're swimming upstream through that current, and it's a positive value versus ground. And in this case, positive is the magnitude, the amplitude of the voltage signal, but we can think of it the same way. It's the fact that we're flowing conventional current through the collector resistor, lowering the potential of the collector versus ground, which is the same reference point that we're using to define V sub B. This negative sign is what gives us our signal inversion. So that negative 180 degrees that we're going to have when we take our V out here is coming from the fact that the collector current is flowing in this direction. So our V out is going to come out here, and our V in through here. So there's the origin of the inversion, just fell right out of Kirchhoff's voltage law and Ohm's law. So real simple. Now remember when we did general amplifier characteristics, we discussed how important it was to understand input and output impedances, because those could really have an effect on whether or not we're going to get all of this voltage gain when we actually draw current through our load resistor, or when we have some resistance with our input signal. This A sub V is our theoretical voltage gain. So we need to define our Z in, our input impedance, and Z out, output impedance, in case we have some non-ideal inputs and outputs. We have a loaded output. The very fact that we have already combined a load resistor here with our collector bias resistor means we've got a loaded circuit. So that's important to know how much that is. Excuse me. So we've kind of already rolled the output impedance loading effects into this definition voltage gain, simply because this R little c has already put the load resistor in parallel. If the load resistor were huge, like 100 mega ohms or something very, very large, it was input into a big an instrument, then R sub L would be huge, and little r sub c would be mostly big R sub c. So we'd want to do that if we were taking a measurement, but if we were using this amplifier to, say, supply another circuit, that wouldn't necessarily be the case. We might have some current flowing. So let's look at input and output impedance for our AC model, and let's kind of walk through that the same way we did in Chapter 6 with the general. So let's start with a review of what input impedance is. So it's the impedance to an AC signal at the input, so it's looking into the circuit from the input here, as it seeks ground. So we're going to think about a signal coming in that has some voltage amplitude, and we're going to say how many paths can it take to ground, and we're going to kind of Thevenize those paths. We're going to say we're going to create an equivalent impedance to ground. So we're going to kind of Thevenize around this input right here. So if we're starting at our input, we can get to ground in one of two ways. One, we can just flow straight through our base resistor, and so that's path number one. Or we can go into the base, into the transistor, and flow to ground over R little e and R big E. So one of those legs is easy. So these are two parallel paths. So path one is easy to define. It's going to be the voltage at this point, which is the voltage at the base, divided by whatever current flows through the base, or flows through this resistor, Ohm's law again. And the path 2 impedance is the voltage at the base divided by whatever current is flowing through both of these resistors. Now remember, I2 is not the same as I1, because this is I2 is flowing through this path, and it's got the full collector emitter current flowing down through the transistor. So we kind of need to define what I2 is so we can get the second impedance, because we can't just use an I1 to define it. So we've kind of already looked at that when we defined the voltage of VB in terms of the collector current. So we know that V sub B, if we're looking at this ground, is just the emitter current, which is pretty much the collector current, times these two series resistors. So we can build our real impedance to ground by using that definition. So we can just plug in our values here. We can use V sub B using this definition, and then use our two different versions of I. And in this case, we're going to define things in terms of just I sub B or I sub C and cancel out. So we can go through some math and put these two paths in parallel and end up with this expression. So our Z in ends up being just the resistance of the base in parallel with this combo. And I will leave you to step through this. This is also in Mr. Fiore's discussion. The only difficult part, other than that takes us away from just being a straight up parallel, is remembering that you've got more current flowing through these two resistors than you would be looking at just from the standpoint of the signal input. So that's why we end up with the beta multiplier on these two. So we have R sub B parallel combo with beta, so the transistor beta, which is very large, times R sub E plus R little e and R big E. So we can do that parallel combo, and that's our input impedance, and we want that to be huge. We want input impedance to be huge. And so now you know why typically when you see circuit schematics for these amplifiers, if you've noticed perhaps, the base resistors tend to be very, very big. So now you know why. It's one of the parallel paths to ground on the input impedance. So we want a high input impedance, so we end up getting a high system gain. So we need that base resistor to be high because it's a direct path to ground at the input. Okay, so now let's look back into the circuit from the standpoint of the output impedance and define a Z out, because remember we kind of want that to be small. So we're going to look at the impedance to an AC signal looking in from the output. So we're going to, the output is of course kind of at the collector point, if we want to look at that. Because, well, let's go back and back to our schematic. The output is here. It's not at the load because the load's already outside of it. So we got to go back to the other side of the coupling capacitor. And so the output point of the circuit really is the collector point. This is signal is going to output there. So we're looking here and going, if I'm sitting at point C, how do I get to ground if I'm an AC signal? Okay. So we'll take a look at that. So we're going to look at point C, which is the output, and say, how do I get to ground? Well, I could flow down through the current source, except I can't because it has a huge impedance. So this is an open. Nope. Path number 2 is not going to happen. My only path to ground is through the collector resistor. So my output impedance is equal to the collector resistor. So generally speaking, if we design the circuit right for a low output impedance, because remember that's going to reduce our loading effects and our reduction in gain due to loading, we're going to want a small R sub C and we're going to want a huge R sub B, generally speaking. So that's how we define gain, A sub V, and our input and output impedance for the common emitter mode. So R out is R sub C, R little c. We will take a pause and then walk through a real example. Okay, we are back and ready to go through an example of a real common emitter small signal bipolar junction amplifier. So here is our schematic. Again, this is the thing you could really build. Not to be confused with an AC or DC model. This is the real deal. And this is where we'll get our values for our biasing supplies. So these are our DC supplies. One here at the collector, and we're going to have another at the emitter in different polarities. We've got our base resistor, 15K, relatively large compared to the other ones in our circuit. We've got a fairly high resistance of our load, so we'll have fewer loading effects, and we've got a fairly high resistance on our collector. So first thing we're going to do is we're going to split this in two. We're going to create a DC model and an AC model, and they are going to overlap at the Q point where we calculate I sub C. So this is how our whole amplifier looks to DC. We got our supply, We've got our big R sub C going into the collector. I just have the BJT here, but really we would have our DC current source and going into the base, and then a diode representing the base emitter junction here. And so we've done several circuits like this, and so we can use the beta, the transistor, which we were given 150, and we can do our Kirchhoff's voltage law loop from the base to the emitter, where we know what that junction voltage is, and use that to get our I sub C, to get our transistor operating point. And conversely, this is what our signal sees. So the signal that we're going to amplify sees this. So we've got our V in. We didn't have that with the DC because that coupling capacitor was an open, but over in the AC model it's a short, so it doesn't even show up here. We keep our base resistor, and here we've got an AC current source and our little RE representing our bipolar junction transistor, and our load resistor and our R sub C are in parallel. And we don't have this resistor because our AC signal goes right through the coupling capacitor, so we only have our 1.8 ohm swamping resistor. Okay, so first order of business is calculate R little e, the emitter resistor of the transistor itself. So we're going to have to get our I sub C operating point from our Q point, and that's the whole reason we did our DC model. So here's a good old biasing DC Kirchhoff's voltage law going from ground, base current flowing through our 15K base resistor. We're going to drop 0.7 volts over our base emitter junction. We're assuming we have a silicon transistor, and then we're going to flow our emitter current, which is approximately the same as our collector current, over a 10 kilo ohm resistor, and we should end up with negative 5 volts at this point. So there's our KVL loop, and then we can express our base current in terms of our collector current and beta, just like we've done before, and we can solve for a collector current of about 0.43 milliamps. So we plug that right into our expression for R little e, which is 38.6 volts to the negative 1 times I sub C, so I sub C goes right in there, whole thing to the negative 1. You can basically start out and create another expression for your 38.6, make this a little easier, but this expression works, and we end up with about 61 ohms for R little e. So that's what we'll put in there. So we can now define our gain in terms of the voltage at point C versus divided by the voltage at point B, and in order to define the voltage at the base, we of course needed R little e, because the collector current, which is similar to the emitter current in AC, just like DC, is going to flow from B to ground. So we needed our 61 ohms down here in our V sub B expression. So we can basically go from ground, and we're going to drop by the collector current flowing over this parallel combo, and that will be V sub C, and that's this expression. So the 13.2 kilo ohms is the parallel combo of 33 kilo ohms and 22, and then we got 1.8 kilo ohms plus our 61 ohm R little e and R big E to define V sub B. We ratio them, the I sub C's cancel, and we end up with negative 7.1 voltage gain, and the negative of course is reminding us that we have a phase inversion, so that's 180 degrees out of phase with whatever signal came in on Vn. So about a 7 times gain in amplitude. So if we had a 100 millivolt signal coming in at Vn, we'd have about a 700 millivolt signal going out, and it would be 180 degrees out of phase. So that's a reasonable gain. We can also apply the formulas we just derived to define input and output resistance. So remember, in the input, we've got the base resistor in parallel with our collector current adjusted expression for the impedance path looking into the base and down to ground, which is this term, V in base, and the whole thing to the -1 because it's a parallel combo. And then again, V out is effectively really just should be the collector resistor. So that is common emitter in a nutshell with an example. So 2 more configurations to go. And I won't go through every single example. I'll refer you to Mr. Fiore's chapter 7. He puts forth a lot of really key concepts in the context of his examples, and I'll try to hit the highlights of them, but there are quite a few. So you'll see a lot of different variations on each one of these different common configurations, but I'll try to hit the main ones here in this lecture without being overwhelming. But definitely worth working through the examples and really just to lock in your understanding of where your gain is coming from and the ways in which you're defining your input and output impedance. This is definitely a place where it's worth going through the derivations. And again, they all fall out of your AC model, Kirchhoff's voltage law and Ohm's law applications. It's very similar to what we did in defining Q point in the DC model. So back to real simple Ohm's law and KVL expressions are going to serve you to get those numbers. Okay, common collector, otherwise known as the voltage follower, for its unity gain for voltage. So here's a schematic, whole amplifier. You could build this. So we got our input signal coming in at the base, and this time we're going to define it with a non-ideal input. We're going to put a little series resistor to represent the fact that our input signal is going to drop a bit before it ever gets into the amplifier. And getting into the amplifier means it's on the inside of your coupling capacitors, which only pass AC. We got our typical base resistor, which we're hoping is really big. And then we're going to have our biasing supply at the collector and the emitter. So we'll have a 2 supply. We're not going to use a voltage divider to provide our biasing. And most importantly, here's where we're going to collect our output. Our V out whoop, is here. V out over our load resistor at the emitter. V out. So we're going to do the same thing we did before. We're going to create a DC model and an AC model of this same exact circuit. So DC model, the coupling capacitors are opens, so it leaves us something we're real familiar with, our 2 supply biased BJT. We'll model the base emitter junction with the diode and assume that we have a DC constant current source between the collector and the base, which we haven't drawn here, but we'll use that Ebers-Moll model, and we'll use this loop where we have all our voltages defined to get our collector current at our operating point. We're also going to use the beta for the transistor, which we are assuming is, generally speaking, you can assume is 100 unless it's otherwise specified. That's a pretty good round number that's common for many BJT devices. Okay, so basically here's our setup that's going to give us I sub C, and I sub C, when we solve for it, is going to be used to define our R little e. So in addition to R little e, let's see what else we did to create our AC model. So we shorted all the coupling capacitors, and we replaced these voltage supplies with direct paths to ground. And in the case here of the emitter, now we've got a parallel path to ground. So the collector is pretty simple. We replace that collector biasing supply with just ground, so that's really easy. The V in at the base looks pretty much the way it did with a common emitter. We instead of a diode, we have our R little e. But when we get to point big E, we have two ways that an AC signal could go. We can go straight through the coupling capacitor and over the load, or we could flow through our emitter biasing resistor straight down through the emitter biasing supply, which looks like a short to an AC signal. So here we go. We have a two parallel paths to ground. So we're going to need to combine these two resistances in parallel when we define the voltage at the emitter or the base from the standpoint of current flowing down from this current source. And so we'll need to do that to define gain. So speaking of gain, how do we define gain? V out over V in again. Well, V in is V base, just like it was in the common emitter mode. But in this case, V out, let's see, where are we taking the output? We're taking it at the emitter. So V out is right here, which when we short the coupling capacitor is at point E. So here's point E. So how would we define the voltage at point E versus ground? Well, it's going to be the emitter current flowing over the parallel combo of this resistor, R big E, and R load. And the emitter current is pretty much equal to the collector current in the AC model, just like the DC. And then the base voltage is going to be the same as the emitter voltage plus whatever the voltage drop of the collector current over our base emitter resistor. So definitely need to calculate this guy. So we've got that defined here. V sub E is emitter current times RERL parallel combo, and then the base is that same thing in series with the base emitter resistor. So not too hard. We can ratio these two down here and come up with this expression for gain. So this parallel combo over this parallel combo plus this defines our gain. So it's like, well, wait a minute, this is supposed to be the voltage follower. It's supposed to have a voltage gain of about 1, and instead of 1, I've got this complicated expression. Well, the thing to remember is R little e tends to be pretty small. The last time we calculated it was about 60 ohms. Depending on how much collector current we're flowing and where we are on that current voltage exponential curve, it can be even smaller than that. So let's assume R sub E, for the sake of argument, is about 50 or 60 ohms. Let's look at the magnitude of this RERL parallel. So for example, let's just scroll down. We'll jump ahead to a typical example. So we have 500 ohms and 10K. So we put those in parallel, and the parallel combo is going to be something a little under 500 ohms. So we're comparing, say, 50 ohms to 500 ohms. Given the typical value for R sub E, it's just going to go away, which is effectively going to leave us with the RERL parallel combo in the numerator and the denominator, which will cancel out and create the big 1 mathematically. So if R sub E is a little bit bigger, then this is a little less than 1. So it's the relative magnitudes of that parallel combo for typical resistor values versus our base emitter resistance in our AC model that gives us that unity gain. So there's our unity gain, almost unity gain, voltage follower. Okay, so we can walk through our circuit and do the same kind of thing in defining our input and output resistance. So we can start with our input resistance, our input impedance, and we see we're going to have a pretty similar situation as we did with our common emitter. Our parallel, if we're looking in at the input, how many ways do I have to get to ground? I can flow straight down through the base resistor, or I can flow to ground, and I can enter the base and I can flow to ground along with a collector current over all of these resistors. So I'll have the base resistance in parallel with this Z input at the base that's going to have a pretty similar way of explaining it as we did for the common emitter. And we can jump right to this expression. So we have base resistor in parallel with beta times everything in this path. So this is pretty similar to what we had before. So let's look at the output impedance, since that's important for our loading effects. Remember, we kind of want that really small. So looking at the output. So it's effectively going to be our big E in parallel with effectively the emitter output, which again is going to be a bit confounded by the fact that we have a lot of current flowing through things. So if we get back up here and we'll just erase, and this is a little bit of a lot of math and circuit analysis. It's actually not a lot of math, it's a lot of circuit analysis. The input and output impedances are definitely kind of the more esoteric parts of this analysis. Gains are pretty easy to calculate, we saw. I'm going over the impedances because as you get further on in your circuit analysis, those become really important in optimizing gain and handling noise. We won't spend quite as much time on that as we do with gain, but I want to walk you through it just once. So our V out is point E. So looking at the paths that we would take, so output impedances is looking at the output point and saying, if I have to go through the amplifier to get to ground, where could I go? I could go here. I'm not going to go backwards because that's outside of the transistor. Or I could go back through here. And good gosh almighty, I can go here too. So from the standpoint of the output, to get to ground, I have a parallel path through our big E, and then I've got this other path where I'm basically swimming upstream against the collector current, and then looking at entering and leaving through the base. So adjusting for the collector current going through our little e, and then the difference between that and the unencumbered paths out this way, we're going to end up having another beta multiplier. So we call that upper path, this path, our emitter out. And it's the effective resistances of R little e, RB, and R gen, given the fact that this collector current voltage source really can influence all of them. And we're not going to step through the proof of it. We're just basically gonna state it as a point of fact and say that the R emitter out is basically going to be the series combo of R little e coming from our emitter point where we're looking into the amplifier, and then plus this Z base equivalent which is again influenced by the collector source. So we had a Z base in when we were looking at input impedance. Now we kind of got a Z base equivalent going out. And we can step through the math, which I'm not necessarily going to go through this time, and we get this formula as a result. So let's just take a look at what things swing this formula. First of all, we got a big parallel path. If our big E is small, it doesn't really matter what the rest of this is. We're going to have a pretty low impedance path to ground. If our E is big, then we've got a fairly low resistance R little e tends again to be pretty low. Then we've got what could be a fairly big resistance in the form of the base. It's going to be in parallel with what's probably a lower resistance going back into our input source, and those are both going to be divided by beta, which is a big number. So when you look at this kind of complicated term in the parentheses, you got a little number plus something divided by a big number. So generally speaking, this term isn't always going to be very big. It's going to be dominated by this one. So that's kind of our takeaway when we look at how to adjust that. So let's put some numbers on something, step through a quick example. So here is a common collector, signal coming into the base, signal coming out of the emitter, and this time rather than having two voltage supplies, we're going to use a voltage divider, a bias supply of 20 volts up at the collector, and we're going to divide that, and we're going to provide the bias to open our base emitter junction by using the voltage drop over this resistor. So we can apply our DC model. So this is what DC sees. Good old voltage divider bias that we've done before. We can assume this is lightly loaded, and so we can basically just say the voltage at point B is going to be 20 volts divided by 22K plus 22K, and then multiplied by 22K, so we'll have about 10 volts at point B. So 10 volts minus 0.7 volts to get over the base emitter junction, minus our collector current times 10K is going to equal 0. And so that will give us our I sub C, and we can get fancy with a lightly or heavily loaded voltage divider, but we can generally assume that I sub B is pretty small. And we get, not surprisingly, a collector current of a little under a milliamp. We can also define all the other currents in that branch. But the important thing for us looking at setting up for our AC model is we use this DC collector current, which is our Q point collector current, to define our R little e, our base emitter resistance for our AC model. And 28.2 ohms, very small, very small. That's why we're going to end up getting a unity gain. So that goes into our AC model along with our load resistor of 500 ohms, our emitter resistor 10K, we got our base, fairly large base resistor, and then our divider drop and our 1K input. It's going to give us some real losses coming in. So we know our gain is V out over V in, and V out is VE, and V in is VB. So we can define an unloaded gain, literally, just using a KVL expression. So we can say V sub E would be just our collector current. If say we took the load resistor away and we just had an open, we didn't let any current flow through the load. Okay, so in that case, V sub E is just going to be the collector current times this resistor. So up here, and of course R sub E is that same collector current times 10K plus R sub E. So almost 1, just shy of 1. But we don't have a full open circuit there. We don't have an infinite impedance at the output. We have a load resistor, and it isn't real big. Remember in our last example it was 33K. This time it's only 500. We're going to get a fair bit of current flowing through that. And in fact, if we apply Ohm's law starting at this point E, we got a 10 kilo ohm resistor here and only 500. More current's going to flow through that load than through our 10K R big E here. So if we were to do that, we would be redefining these two numbers based on, in the case of V sub E, as the parallel combo of this 10K and this 500, and that turns out to be just shy of 500 and on the top, and then just shy of 500 plus 28 on the bottom, and so we get 0.944, so a little less, as expected. When we include the effect of current flowing over our load resistor, we reduce our gain. No, it wasn't very big, it was almost 1, it wasn't huge, but we reduced it, going from the unloaded to the loaded. Now we have one more hit on our system gain, and that's our 1K input resistor. So if we wanted to take that into account, we would have to admit to ourselves that our input voltage VB was not the same as VN. It was really Vn minus the voltage drop over this. So we would have to take into account this voltage divider. So we'd end up reducing our system gain even more if we included that input. So hence why we want this resistor to be huge, because then we limit this current path and this stays high. And of course, staying high also helps us open the base emitter junction, so two jobs in one. We can use the equations we just developed for Zn, just apply those, and notice we have a 50 kilo ohm input impedance. Again, we've got our base in parallel with our Zn base in this case, but we have another 22K. So why do we have three things in parallel for Zn? Because when we defined it the last time, there were only two. So remember, input impedance is all the paths a signal can take to ground when it pokes its nose into the amplifier from the input. So we're going to start here. We're going to say, from this point right here, how can I get to ground? Well, I can flow through the base resistor, so that's 22K, so there's this one. I can do this funky path through the base input of the transistor, where I have to multiply by the beta, my Zn base, but I can also get to ground by flowing back up to the collector, because that bias voltage source at the collector is no impediment to an AC signal, and I can flow to ground through the DC supply at the collector. So I have a three-way path. So I have this 22 kilo ohm resistor in parallel with this 22 in parallel with this Vn base. So it's a three-way parallel, and it still gives us 50 kilo ohms. So V out, we have that same situation where we can flow straight to ground through this 10 kilo ohm resistor, or we can have this R emitter out flowing over R sub E, and then we can go from this direction and then all the way back, multiple paths. So we have a three-way, but those are subject to the beta. So this number ends up being really, really small. And because this is really, really small, it's in parallel with something big, this one actually determines the output. So we end up with a really low output resistance, and that's what we want to reduce our loading effects. So this is a good thing. We have a high input and a low output. So that is a well-designed amplifier to reduce loading effects. And this little sketch is replicated in our textbook as just an easier way to show the effect of the input voltage divider. So this is kind of a repeat of chapter 6, voltage inputs. Okay, we can, if we need to get really, really high current gains or voltage gains, we can always double up on our BJTs. We can always cascade the output of one emitter or collector into the base of another. And this is what's known as a Darlington pair. It's when we have two transistors in what's called a cascaded configuration. And they're particularly useful and natural to use with the common collector configuration, because you can just literally flow current directly down through both. So our collector is up here, our emitter is down there. So with these this ganged pair, Darlington pair, we would have our signal come in at base 1. We would we would realize our beta gain of this transistor, and that amplified signal would then be the input to the next one, and it would gain beta, and then finally come out to our output. So, important thing to note, the gains of cascaded amplifiers multiply. So, beta for a typical BJT is 100. 10 to the second, now we have 10 to the fourth. Beta is huge. We won't realize this with voltage gain, because it's the common collector. It's still going to have a gain of 1, but we're going to get an enormous current gain out of this. So if you needed a lot of power, you needed a lot of current for something, this is going to do a lot of good for you. We do need to take into account the fact that we're going to have two base emitter junction potentials from the point of our DC model. So instead of 0.7, we're going to drop 1.4 as we go from our first base to our second emitter. And of course we're going to have now two R little e's when we do the AC model of these base emitter junctions, but we just put them in series because they are in fact in series. So very, very simple to model. Gains multiply. We add the effects of the voltage drops from effectively the diode portions of our DC model, and we put our two little REs in series, and we can treat that pair as if it's just a single BJT. So you can step through example 7.5, goes through that, and you can see here on our AC model we basically have two R little e's, and here we're going to be, when we go through and calculate our collector current, we're going to be looking at, instead of a 0.7 base emitter, we've got a 0.7 plus a 0.7 drop. So that's the effect of the pair seen. The biggest effect comes from a great big beta, 10 to the fourth. And that will be felt in our input and output voltages every time we have that beta multiplier on one of those parallel components. We'll now either drastically increase something or drive it into the ground. So that's the Darlington pair being used as the actual BJT component of a common collector. Okay, we'll not step through more of that. Common base. This is our last common configuration that we'll go through. So remember, this one gives us a lot of voltage gain, but unity current gain. So let's see, let's walk our way through. How do we define common base? It's defined as voltage input at the emitter, which we got right here, and output, here's our load, is output at the collector. And it's easy to see why it's called common base, because in this case the base is literally at ground or common. Okay, easy to look at the DC model. We've got a collector voltage supply, so we'll have collector emitter DC current flowing down to whatever voltage is defined by our emitter supply. So we've got a two supply biasing scheme. The base is at ground. So we know that this emitter has to be a negative versus ground to open our base emitter junction, because current has to flow this way. So in this case our collector point is at, from a DC standpoint, is below ground, which is fine. We can put those supplies in any way we want. And the easiest way, and I will zoom in on this a little bit so we can see it, the easiest way to approach the AC model of common base is to redraw the circuit horizontally, just rotate it on its side. So here's our transistor AC model. We've got a collector, and we've got our AC current supply between the collector and the base. Here's our base connected to ground. So base current would flow from the base point to ground. Here's our collector. Collector current's flowing in this direction from our current source. And here's our base emitter junction being represented by our R little e as usual. Here's our emitter AC current, which is going to be approximately equal to our collector, flowing out the emitter. And the rest of our model is basically going to use the same rules we've used elsewise. So when we get to our emitter, we've got coupling capacitor shorts, and there's our input source, and we can look over here at our supply. At our collector will be a short to ground. We have our things in the right place. Yep. Our load is at the collector, so here's our output. So current's going to flow from ground over the load and over R sub C. So V sub C is going to be a bit below ground in that sense, and we're going to have input current flowing in this direction. So basically we have two negatives that cancel, so we don't get an inverted signal. So let's define output and input so we can define gain, and we'll get rid of some of these current arrows. The horizontal configuration is really makes it easy to look at this and do our calculations without getting lost in the fact that we don't have an input signal coming in at the base like we're pretty much used to seeing. We're used to really defining current gain in terms of base versus something else, but that's not necessary. So we're gonna follow the rules that we've established with our AC model and just step through. So we know that current is going to flow in the direction of the arrow of the current source, so we know that we've got our collector current flowing in this direction from ground, dropping over this resistor, and it's going to continue to flow over our emitter, our base emitter little resistor, our internal resistor, and then to ground through this resistor. So, and the input will flow in the opposite direction. So our V out is V sub C, and so that's just going to be our collector current times effectively our collector bias resistor. And V in, this point, is equal to V emitter, because they're connected by a wire here. So we need an expression that relates the voltage at point E to ground. We can use this voltage, which is the base point, to help us define, that's a B. This is the base in our AC model. So there's a R little e between the emitter and the base. This is just horizontal configuration of the same AC model. We know that the emitter current flows between the base and the emitter through the BJT over our R little e. Well, the base is grounded, so the base is at 0 volts, effectively defined as ground. So the emitter point is 0 minus emitter current times R little e. So effectively, these are both negative numbers, and that's why we don't invert. Current is flowing from ground and going down in both cases. So our V in is defined as point E, because there's just a wire connecting those. Point E can be defined in terms of ground as just swimming upstream the emitter current over R little e. So our voltage gain is big R sub C, our collector bias resistor, divided by R little e. Remember, this is really, really small. So we tend to have a fairly big bias resistor divided by something that is probably only going to be, what, 20 or 50 ohms? So hence the big voltage gain of common base. And of course, this ignores loading effects. If we were loaded, this R sub C would be replaced with the R sub L, R sub C parallel combo, and so this number would go down, so our gain would go down just a bit. And so here's our origin of the big gain. If we want to define input and output impedances, they're even easier. Our output impedance again is from here's our output. Because we can't go through the current source, that's infinite impedance. Our Z out is just R sub C. And if we're looking at our input impedance, we could flow to ground through this path, or we could flow to ground through this path. And we will have just those two in parallel with one another. So really simple expressions for input and output impedance. So unfortunately, R sub C tends to be kind of big, so we're going to have big output impedance, not so good. But our input impedance should be very, very tiny because we've got a parallel path that goes through this tiny base emitter resistor. So we shouldn't lose much input signal with our input voltage divider in that sense. So that's common base. Again, use the horizontal model if you're given a vertical schematic to make it easier to draw your AC model. Or you can draw your AC model vertically, it doesn't matter. But use your AC model and DC model. It doesn't matter where your signals are coming in and out. Use those models. Use your DC model to get your collector current, your DC collector current. It's the Q point. Your AC collector current is the same as your DC collector current at the Q point. They're the same. Use that to get your R little e, and then it's Kirchhoff's voltage law all the way. Define your gains, decide if you need some loading effects, and I would highly advise that you refer back to your text or your notes to get those expressions for input and output impedance there. They do require a little bit of thinking, especially if we're to do the beta multipliers. But otherwise, just the AC and the DC models working together at the Q point, defining our gains in terms of V out over V in, and knowing which voltage point versus ground is out and in, which is pretty easy looking at your AC model. So that is it for small signal amplifiers with BJTs. We are not going to look at their analogs with field effect transistors. That's out of the scope of this course, but just be aware that the same types of small signal amplification can be achieved with field effect transistors, but all of the effects of the circuits are a little bit different because of the very different operating nature of field effects. We don't have necessarily a base emitter junction. Remember that the gate source voltage is the controller for field effects, and so you're going to have a very different circuit setup, but you could walk through all of the same types of arguments starting all the way back in biasing and come up with very analogous expressions for gain if we started with a field effect and its primary characteristics. So can be done, and there are definitely advantages and disadvantages to both types of transistors. So there are amplifier circuits made from both, and those we will probably just work with later on in operational amplifiers, and a lot of those distinguishing characteristics will be rolled into the specs that we will simply buy and utilize and have fun with. So see you then.